Hey guys, this particular problem represents us moving toward the culmination or the end of this unit. When you're doing these types of problems, you'll see there's many points to them. You kind of have to have a real sense of awareness as to what exactly we're talking about. If we're doing a titration, where on the titration curve is the specific question referencing? Because how you answer it is determined by your level of awareness. Are we at the equivalence point? Are we at the half equivalence point in the buffer region? Because we use different math depending on where we are in the scenario. So let's take a moment and look at the equation above. This references ammonia, which you should recognize as a weak base at this point. When you put it in water, the reason why it's a base is because it scavenges that proton from water, giving us ammonium and hydroxide ions. So that's why the solution becomes basic. As we read the problem, in the aqueous solution, ammonia reacts above. In 0.0180 molar ammonia, 25 degrees Celsius, the hydroxide ion concentration is 5.60 times 10 to the negative 4 molar. In answering the following, assume that the temperature is consistent at 25 degrees Celsius and that the volumes are additive. So, first and foremost, if I'm thinking about this and making a rice table, I would say to myself, I already have something to plug in at the equilibrium position, and that's going to be this 5.64 times 10 to the negative 4. And we'll see if that actually comes into play later. But as I read a problem, I try and think things through a little bit and sort of pre-guess what they're going to ask me. Part A asks, write the equilibrium constant expression for the reaction represented above. And in this case, this isn't Ka, but Kb, right? Ammonia is absorbing a proton, so I'm going to call it Kb. Although, honestly, if you just wrote K, you'd probably still receive full credit for this. But we're recognizing that it's a base. So in our expression, we have ammonium, NH4 positive, and we have hydroxide, OH negative, divided by ammonia, and did you get it right? We're not going to include water because it's a pure liquid. Part B asks to determine the pH of this 0.180 molar ammonia solution. Well, in this case, if we're asked to calculate the pH, we actually know that at equilibrium what the OH negative is. So this actually is a pretty simple problem so far, in the sense that if I've got the OH negative, I can calculate the POH and just subtract from 14. So the OH negative concentration, as shown in the problem, is 5.60 times 10 to the negative 4 molar. As we remember, the P of anything is the negative log of that thing. So the POH is the negative log of this number, 5.60 times 10 to the negative 4. And when you plug that into the calculator, we should get 3.25. So to calculate the pH, because we know that the pH plus the POH is 14, this becomes a simple subtraction. Thus, the pH is equal to 14 minus 3.25 to give us a value of 10.75. for our pH. And once we have an answer, we're going to ask ourselves, does this in fact make sense? Well, we're expecting it to be above 7. It is above 7. It's not at 14 or 13 where the strong base, but a weak base, so this actually makes total sense. Let's scroll back up and look at part C. Determine the value of the base ionization constant Kb. Well, when we think about our expression, we could write out a Rice table, but in our reaction, if we know that this concentration right here is in fact the 5.60 times 10 to the negative 4, we also know something else, that whenever this is made, the ammonia is made at the same time. And assuming that this number is, because this number is very small at 10 to the negative 4, we could use the assumption that the concentration of the ammonia minus this x, right, is so small that in fact it's negligible. So for part C, we're going to reference again our Kb from part A, NH4 plus times OH negative over ammonia and honestly, we don't even need to use the Rice table here. What we're just going to do is we're going to insert the concentrations, and because of course the ammonium and the hydroxide are the same, this number simply gets squared. So 5.60 times 10 to the negative 4 squared over our original concentration of 0. Looks like it was 0.180 molar. 0.180 molar. And of course, in theory, using a Rice table, we might show this, as a subtraction of this exact number here, but because it's so small, we're just going to assume that 0.80 minus 5.60 times 10 to the negative 4 is in fact just 0.180. So we're just going to make that assumption, and then we're just going to solve using our calculator for the answer. And what I get is 1.74 times 10 to the negative 5, which is a pretty small number, consistent with our answers so far. Let's return now to read the next part of the problem. Determine the percent ionization of ammonia. Well, the percent ionization is going to tell us basically what molarity is ionized minus what was the original molarity. And so to answer this question, for our percent ionization, how much in fact is, so the molarity ionized over the molarity initial, or the molarity total. We could also use moles here because it's the same solution. So the percent ionization is simply the part over the whole times 100, right? Because percent is always part over whole times 100. When you do the math on this, you should get 3.11%. All right, now let's look at part D, or part E, where it's getting a little more difficult. In a separate experiment, we titrate a 20 ml sample of our base with 0.012 molar HCl. and it's been titrated to the equivalence point and beyond. Determine the volume of the HCl that was added to reach the equivalence point. Now this is a different chemical reaction, right? This is HCl with NH3, and it looks like in order to solve this problem, the first thing we should do, of course, is write the balanced chemical reaction. Instead of just NH3 and water, right, we now have NH3 mixing with HCl. And it's not a double arrow, but because HCl is a strong acid, this reaction goes to completion in the Bronsted-Lowry sense. There's a full transfer of the proton onto the ammonia to give us ammonium and chloride. So here's where the balanced chemical reaction is needed, knowing that it's a 1-to-1 reaction between the ammonia and the HCl. So the way to solve this problem, right, is to recognize, well, if I have my ammonia below, the number of moles of ammonia that are down here equal the number of moles of HCl added at the equivalence point. So therefore, because it's a 1-to-1 problem, all I really have to do is figure out the moles of ammonia and then relate that to the moles of HCl using its molarity. So to start with this, I'm going to use the molarity of the ammonia solution. So we have a 0.0180 moles of ammonia. And I took, my sample size was 20 mils, or 0.0200 liters. And if I multiply this out, I would get the moles of ammonia down below. However, I want to relate that to the moles of acid. 1 mole of HCl will react with every 1 mole of ammonia according to our balanced chemical equation. And then lastly, I'm not going to write the molarity of my acid straight up. I'm going to write it inverted, because if I write inverted, then my moles of HCl will cancel. And what I'm left with is the volume of acid needed to equal or get to that equivalence point, because at this point the moles of acid added are equal to the moles of the original number of moles of base present. Once I incorporate that last number, I just multiply it all the way straight through, and the molarity of my acid solution was different than the base. It was 0.0120 molar HCl. Working this all the way through, multiplying 0.0180 times 0.02 divided by 0.0120, I should end up with the number of 0.00 0.0300 liters of HCl added. Quickly scrolling back up and looking at part 2, determine the pH of the solution after a total of 15 mils of my acid have been added. What's an interesting point there to make is at 15 mils, now here's where your awareness has to come in. 30 mils was my equivalence point. So if I were to look at this in graphically, 30 mils is my equivalence point, the point at which the moles of the acid added equal the moles of the original base. 15 milliliters is right here in the buffer region. The buffer region where half of the ammonia has been converted into NH4 positive. When you're doing this type of work, here's where you must say to yourself, well, I'm in the buffer region. And if I'm in the buffer region, the way to solve the math here and answer what the pH is to use the Henderson-Hasselbalch equation. So pH is equal to pKa plus the log of the base over the acid. We're in a very convenient point along the, in the buffer region. We're at exactly half. And at exactly half, because the base and the acid are going to be the same concentration, this of course reduces to the log of 1, which is 0. If we were either to the left or to the right of that 15 at around 13 or at around 17, we would still use the Henderson-Hasselbalch equation, but this would not be an equivalency of a ratio of 1. And the way you solve those types of problems is you would do a Rice table, and instead of using molarity, typically when we're doing titrations, because the volume is constantly changing, we do a Rice table with moles. And so you would insert, with Rice, the reaction, the initial, the change. I mean, the E isn't really equilibrium, but more like the final state. Because, again, this is not, an equilibrium. This is a quick reaction in which it is totally to the right because we are forcing the proton onto the ammonia using a strong acid rather than just water. So you'd input the initial moles of NH3 that we had already figured out above, 0 for HCl to start, 0 and 0 product. And then we would move down. What are our changes? The changes are, at this point, at 15, if we were to do 14 or 17 mils, we could figure out exactly how much of the acid has been added and then exactly how much of the base remains. And that's where you would plug in a ratio here of moles. You could do molarity, but if moles per liter divided by moles per liter reduces actually to a mole-to-mole ratio if it's the same solution. You could actually just plug in your moles there. But in our case, we're in a very fortunate scenario because the pKa and the pH are easily figured out from the Kb above. This video is getting a little long, so I'm going to continue with the part 2. I'm a little afraid YouTube has a time limit.